In this video, we will look at Vieta's formulas, which relate the roots of a polynomial to its coefficients. Let's see what it means by that by taking a look at the most well-known form of Vieta's formula, which is the quadratic case. So let's start off with the general form of a quadratic expression, ax squared plus bx plus c. And let's say that this has two roots, r1 and r2. These are its two distinct roots, or they can be the same. So if they are indeed the roots, then this quadratic can be factored in the form a times x minus r1 times x minus r2. And so because factoring does not change the value, these two expressions are equivalent. And so if we expand this, we should also get an equivalent expression. Expanding the factored form gives you ax squared minus ax r sub 1 minus ax r2 plus a r1 times r2. And we can further simplify this by writing it as ax squared minus, or plus, actually, plus x times minus a r1 minus a r2 plus a r1 r2. And so because these two are equivalent, that means c over here should equal this, and b over here should equal this. And let's write that information down. So based on what we just said, b is equal to negative a r1 minus a r2, and c is equal to a r1 r2. And now, in the first expression, we can factor negative a out to this, and we can divide both sides by negative a to get negative b over a is equal to r1 plus r2. For the second equation, we can just divide both sides by a to get c over a is equal to r1 times r2. These two expressions are the Vieta's formulas for a quadratic equation, and it holds for all quadratics. It tells us that the sums of the roots of any quadratic is equal to negative b over a, and the product of any two roots of a quadratic is c over a. And let's take a look at how we can apply this. First, let's look at a super basic example. X squared minus 5x minus 6. And you need to find the sum and the product of the roots. Well, for the sum of the roots, r1 and r2, we know that's equal to negative b over a. And here, b is 5 and a is 1, so it's equal to, b is negative 5 and a is 1. So it's equal to negative 5 over 1 is equal to 5. And the product of the two roots is equal to c over a, which is equal to negative 6 over 1, which is equal to 6. And now let's verify our solution is correct by actually factoring this expression into x minus 6 times x plus 1. And we see here that the two roots are x is equal to 6 and x is equal to negative 1. 6 plus negative 1 is indeed equal to 5, which matches what we have here. And 6 times negative 1 is equal to this should be negative 6. Is equal to negative 6, which is what we have here. So we see that Vieta's formula holds. Now let's look at a slightly trickier example. 2x squared minus 7x plus 12. And you want to find out the value of r1 squared plus r2 squared. So the sum of the squares of the two roots. And so it's not immediately obvious how we can calculate r1 squared plus r2 squared. But we know what r1 plus r2 squared is. So let's take a look at what happens when we square r1 plus r2. Well, this is just equal to r1 squared plus r2 squared, which is what we want. But it also has an extra 2 times r1 times r2. So if we were to just subtract this from both sides, we would have our desired expression, r1 squared plus r2 squared. So now let's subtract that from both sides, and we get r sub 1 squared plus r sub 2 squared is equal to r1 plus r2 squared minus 2 times r1 times r2. And so now we just have to plug in numbers to find what r1 plus r2 and what r1 times r2 is. And we can get that through Vieta's formulas. So r1 plus r2 is equal to negative b over a, which is equal to 7 over 2. r1 times r2 is equal to c over a, which is equal to 12 over 2, which is equal to 6. And now we can plug those numbers into what we have here. So r sub 1 squared plus r sub 2 squared is equal to r1 plus r2, which is 7 over 2 squared, minus 2 times r1 times r2, which is 6. So this is equal to 49 over 4 minus 12. But instead of writing it as minus 12, let's write it as 48 over 4, so we have a common denominator. 49 over 4 minus 48 over 4 is just equal to 1/4. And so that is our answer, and we can see that the sum of the squares of the two roots is just equal to 1/4. And we did this all without actually finding the two roots. So let's look at one more example of the quadratic case. 3x squared minus x plus 16. And we want to find the sum of the reciprocals of the two roots. So 1 over r1 plus 1 over r2. Well, let's first get a common denominator. So we can multiply this first fraction by r2, which gets us r2 over r1 times r2 plus, and here we can multiply numerator and denominator by r1, so r1, r2. And now we can combine to get r1 plus r2 over r1, r2. And we know both what this and this are by Vieta's formulas. And so let's just do that real quick. So r1 plus r2 is equal to negative b over a, which is equal to 1/3. This product of the two roots is equal to c over a, which is equal to 16 over 3. And now we can just plug this in. So we have 1/3 over 16 over 3. And now this is equal to 1/3 times 3 over 16, taking the reciprocal. And this is equal to 1 over 16. So we can say that the sums of the reciprocals of the roots is equal to 1 over 16. But what about Vieta's formulas for higher degree polynomials? For example, what about a cubic? Ax cubed plus bx squared plus cx plus d. Well, it turns out, this now has 3 roots, r1, r2, r3. It turns out that the sum of the 3 roots is still negative b over a. And also, no matter what degree your polynomial is, the sums of all of your roots will always be equal to negative b over a, even if you have like a 99 degree polynomial. So that's useful to know. What about the product of the two roots? Well, now it's equal to negative d over a. And so you'll notice that it's still your constant term over your leading coefficient, but now the sign has switched. And you can generalize this for any degree polynomial where you can conclude that this product of all your roots is equal to negative 1 raised to the nth power, where n is the degree of your polynomial, times your last term over your leading coefficient of your first term. So for example, if I have a fourth degree polynomial, ax to the fourth plus bx cubed plus cx squared plus dx plus e, first of all, it's a fourth degree polynomial, so the product would be negative 1 to the fourth power times your last, which is e, over your first, which is a right here. And negative 1 to the fourth power is just 1. So that means that your product of two roots, or product of all your roots in a fourth degree, is just equal to e over a. So just keep in mind this generalization with the products. With cubics and above, though, something else also happens. Instead of just the sums and products of all your roots, it also starts choosing like two of your roots and multiplying them and adding all possible combinations. So in terms of cubics, there's also a formula telling you r sub 1 times r sub 2 plus r sub 1 times r3 plus r2 times r3, where essentially it chooses two roots, multiplies them together, and adds all possible combinations. And in a cubic, and so if you're choosing 2, it's always going to be equal to c over a. In a fourth degree polynomial, it's possible to choose 3 roots and add all possible combinations. Like so, n plus, for example, r1, r3, r4, and all possible combinations, that's equal to negative d over a. Choosing all possible 4 combinations is just equal to e over a. And I think you see a pattern here where it's always last over first, or it's just C, D, E, F, G, so on and so forth, but the sign flips every time. So that's pretty much what Vieta's formula is. It relates the sums and products of the roots to its coefficients.